Good afternoon, everyone. I'm Dimitri Peroulis, the head of ECE, and it's my pleasure to, pass the baton to Tim Rogers. So Tim is an associate professor in our school. He is actually working in the areas of hardware and software engineering, and specifically on programmable accelerators like GPUs. Tim is really the recipient of many different awards. He has won many research awards, teaching awards, best paper nominations. I'm just only going to mention that he has won the NSF Career Award and the College of Engineering Exceptional Early Career Teaching Award. So right now, Tim is working in expanding the reach of efficient hardware in the twilight of Moore's Law, and the rest will be on his talk. Thanks, Tim.
Thank you very much, Dimitri. And thank you all for having me here. It's kind of an interesting presentation to create and give, and I'm glad to have the opportunity. So like everyone, I'm going to start off with my origin story. My map's a little bit bigger than the first presenter, but not as big as the second presenter. So I'm from Canada, that little rim of land right above the US here. And I was born in the small Canadian province of Nova Scotia to two loving parents, Anthony and Colleen Rogers. And I grew up, most of my life growing up, I was raised in a very small town of about 800 people called Chester, Nova Scotia, on the coast of the Atlantic Ocean. I had a happy childhood. I spent my winters playing hockey like a stereotypical Canadian, my summers playing baseball. I was never good enough at either of them to play beyond high school, but I was pretty good at school, so I decided to keep going with that. In 2001, I graduated high school. And then I decided to move on and study. And for someone in my field, I'd never actually programmed a line of code at that point in my life. I just liked math and I liked science, and I was like, okay, I'm going to go do something interesting and build things. And so I went and I decided to go to a college called McGill University in Montreal. And this was a huge jump for me, coming from a town of 800 people into, I know many people from Asia are from giant cities, but to me, Montreal was a giant city. Several million people, huge French influence there. And I spent, 4 years studying electrical engineering, which is not actually what I ended up doing now. And I actually did an honors degree there. I wrote honors here for two reasons. One, we spell it weird. There's a U on there. And every time I write my CV, Word complains at me because that's the British way to spell it. In America, you don't use the U. And I had an advisor there that I actually, did my honors thesis with, Dr. David Plant. And I did my honors thesis in something very far away from what I'm doing right now, the optical reception of gigabit Ethernet, which was huge in 2005. And it was a very analog type of thing, and I ended up sort of veering into the digital world. And part of the reason why I did that was I thought that analog stuff was super interesting, and Dr. Plant was also okay with me signing off on my honors contract after the deadline had passed, because I'd actually I'd put it off too far, and he allowed me to to research with him, even though I'd passed the university deadline. So anyway, I studied electrical engineering here, and then I decided to not go to school right away. I was ready to go make some money and get a real job. So I actually moved to Vancouver, Canada, so still staying above this line, over on the West Coast, and I actually moved with no job. I moved there because my wife got into pharmacy school, and I just followed her there. And I was unemployed for a few months, and was trying to find a job. And I found a job, and I put real job in quotations here because I actually made video games. It was a real job, and it was actually a really fun job. I worked for Electronic Arts. They have a big development office in Vancouver. And I worked there for about 5 years, and it was actually a lot of fun. It was a super fun job. They have a soccer field and an inline hockey field and basketball courts you can go play at lunch. And I played in intramural leagues in between coding up these games. And it was actually a pretty cushy, nice job, and I liked it a lot. And then I got promoted, and then I decided to quit because I'm not if you're passionate about video games, this is where you should be. But I wasn't passionate about video games. I really wanted to understand machines better and try to make them more efficient. That was what the most fun part of my job was. So I decided to go to graduate school and pursue a degree in computer architecture. And so I went to graduate school in the same city. I actually took the bus out to talk to my future advisor from my job at Electronic Arts, and we seemed to have see eye to eye. Professor Tor Amat, he was my PhD advisor, and I applied and then got in, and then went to school here in Canada, out here at UBC. and I spent 5 years doing my PhD, during the course of which I got to do some pretty cool internships. I went down to Seattle to do an internship at AMD Research. I didn't put pictures on here of all the folks who I'm going to call out. So I worked with several folks there, Brad Beckman and Gabe Lowe at AMD Research. Gabe is now a fellow there. And then also worked down in Texas at NVIDIA, mentored there by a guy named Steve Keckler, all of which who's had vast influence in my choice of problem and just trying to understand what it's like to be in industry and what it's like to innovate in this space. So I did that, and I finished my graduate degree, and then straight out of grad school, I interviewed and managed to score a job here at Purdue, and I came here in 2016. Oh, and I also mentioned that while I was a grad student, I also had 2 kids. My wife and I gave birth to my daughter Erica in 2011, and then my son Nate in 2013. These are their first Halloween costumes. That's why they look strange. One was a sunflower, and Nate was a peas in a pod or something. I don't know. My wife picked them out, but I thought, they were kind of embarrassing pictures. They haven't seen this presentation. That's okay. So yeah, that's sort of my journey on how I got here. So they gave us a list of questions on like what you're supposed to put in this talk. And so one of the things is like, how did you get the job? And if I'm being completely honest, and now I have tenure, so I can be completely honest, I got this job because of my very first paper. It's the paper, it went on to win a whole bunch of awards, it won me a bunch of fellowships, independently funded my PhD, et cetera. My most cited paper, people in the field probably think about this paper when they think about my work. And so, I obviously did a bunch of other stuff in graduate school, but that paper is the reason I got top 10 interviews. And I bring this up because, that paper, the story of that paper is not all smiles and sunshine. We did that paper and we submitted it. It took a lot of work. It took like a year and a half. We submitted it, and then this is an empirical field. We found a bug in the code that we wrote that studied the design of the paper, and it changed the results. And it changed the results in a negative way. And we had to withdraw it. So we actually had to withdraw the paper because the results were wrong. And the idea was actually dead for like 10 months. And my advisor said to me at one point that this is actually a sad little paper. Now, I love my advisor. I'm not, and I have a very good relationship with him now. And if I reminded him that he said this, he might not remember it because it's also one of his, landmark papers. But this is sort of, it was a really trying time, right? We submitted this thing, and we thought it was going to work, and then we had to withdraw it because of an error. But I stuck with it in the end. I didn't give up on it. I kept pushing on the idea. And actually one day while I was running, and this is a piece of advice I'd like to give anyone who's trying to do any kind of creative or deep piece of work, exercise, right? Exercise is one thing that I love to do, and I love to like think about things while I'm doing it. And I actually came up with an idea to save the paper. So something we had done, we could change, and when we changed it, the results got better. And then I sort of worked on it, and I worked on it actually at night when I was an intern, because I got this idea when I was interning and working for AMD during the day and then working on this paper at night. We submitted it, and then it got in, and then sort of the rest is history. So, I think that one of the questions here is like, how do you succeed? And one of the things that I want to sort of point out on how, what I think it takes to succeed is to just keep trying. Okay, there's this actual trend on Twitter, academic Twitter, of like posting all your rejections, right, of like things. So, that was a huge, life is not just one sort of unbroken stream of successes, right? And when I first became an assistant professor, and I think many of us have these same stories, you submit, you get rejected. My first 7 grant applications all got rejected. 15 pages worth of work, a whole bunch of mental effort, and it didn't work out. And then eventually it hit. And then once they started to hit continuously, and then things got a lot better. So just sort of persisting and trying to find a way to make something work is really the best piece of advice that I can give you generally in any technical field. Don't give up. There's always a way. Just keep pushing at it. And that's really what has made me able to succeed. And I really do owe this to my parents. All these intangibles that people have about themselves, this comes from my background of my parents sort of teaching me that you don't give up on things. Keep pushing. And the other thing that I think has been helped me succeed is to be really passionate about creative ideas. When I come up with an idea and I publish a paper, I feel like a rock star. I know society doesn't see us that way, but I feel that way. And I have an anecdote actually that sort of nicely matches this. A couple days after I submitted that first paper, I went to a rock concert with my wife, she was my wife at the time. She was actually pregnant with my first child. And the guy on stage was talking about like their career, and they were saying that like they were playing in garages, they were a couple years, milling around, nothing was hitting for them. He thought about like going back and working as a janitor or something. And then he wrote one song, and it took off, and then they were super famous. Okay, and I felt that connection with what he was saying with the research I had been doing. That it was like I was milling around, trying really hard, and then I did one thing, and I felt like that thing was going to take off. And it turned out to actually be true in my case. Ever since, every idea, I sort of feel this passion that like I'm inventing something. My name is on this thing, and I think it's pretty special. Another thing that's helped me to succeed is to do stuff that if you thought about it for a really long time, it's probably a bad idea. Okay, so quitting my cushy job that I really loved to go back to graduate school. A lot of people thought that was a stupid idea. I talked to my colleagues, like, why are you doing this? I actually went back unfunded. In Canada, the funding situation is a little bit different, but I decided just to do it anyway, because I wanted to. And I love the fact that I did that, because it set me down this career path. Having kids as a poor grad student, many of us maybe have done that. People told me that was a stupid idea too. One of my favorite things I've ever done. Pushing on an idea, even when your advisor said that maybe it's a sad little paper. Now again, I'm bagging on my advisor, but I love the guy. If he hadn't said this, I probably wouldn't have kept pushing on it. Just my personality, right? I want to prove that he's wrong. And that sort of has been good for me. And even moving here, right? I'm a Canadian, I went to school in Canada. Moving down here with my family and everything was sort of a jump. So everything that I've done, all the favorite things I've done, I sort of just did them and sort of dealt with the consequences afterwards. And I think that those are the things that I enjoy the most. So I managed to talk for over 5 minutes and not talk about anything about what I do. So obviously that's why I'm a professor. So what am I passionate about? So what do I actually do? I do computer architecture. So what I do is I design systems and the hardware that runs those systems that really power the world. It's a very empirical field. Like I said, we can have bugs that can make your results incorrect. And the nice thing about it is that what we study really depends on what people are running for software. So these last two folks that had really cool things that they were doing, that's driven by software that's running on hardware. We're sort of like the money of science, right? Like economists, sort of try to figure out like where the money is going to go. We're providing the computation that's going to allow science to do whatever it wants, right? We're sort of embedded in everything because everything runs on a machine, and how that machine is built is determined by us. And I love that fact. And that means that it's always changing, always moving. It's never static. There's always going to be something new that comes up. Now it's machine learning. Thank God for machine learning, from a sort of interest in our field perspective. But it sort of continues to push things in weird new directions that we can design new hardware for, which is exciting. So what does my research specifically look at? So there's this general tension between how easy a machine is to use and how efficient that machine is. So I've thrown a few design points out here of typical types of machines you might see. Up in the top left-hand side here is something that's really easy to program, which is like a traditional CPU core. For anyone who's ever programmed before, this is probably the first thing you ever programmed on. There's actually a lot of really smart stuff in the background trying to make that run well. But it's not super efficient. You can go the other way, be a hardware designer, and know exactly what you want and specify it and build an ASIC for it, but that's really hard. So only a subset of people that can really do that well. And there's all these designs in between. So what we're generally trying to do is create a piece of hardware that's efficient, but that isn't so challenging to program. And there's a whole space of different things that we can explore there to try and make that happen. So, it's not a research talk, so I just want to give you a flavor of some of the things that we do. So one thing that we took a look at is, could we run object-oriented code on a GPU? So anyone who's ever programmed before, you maybe programmed in an object-oriented language. Does that work well? Well, no, it doesn't work well. So you can come up with some clever tricks to basically optimize that program to try to make it run well on that really efficient piece of hardware. We also study giant hierarchical machines. So, as machine learning in particular gets more demanding, it needs more compute. We need to stitch a whole bunch of machines together to do something useful. Those machines are now being composed of these things called chiplets because Moore's law is ending and it's really hard to make big chips, so we have to make bigger chips out of little ones and then put them together on a substrate. What does that do to programmability? How do we make that work well? And then finally, the most recent thing we're doing is actually looking at different types of accelerators in the data center. So outside of machine learning, which is obviously driving a lot of this, all of the web services that you use on your phone, et cetera, are running with these things called microservices in the data center. Could we develop accelerators for these things? We think the answer is yes, and we've got some work in that direction. So coming back to sort of a more higher level point, why do I love this job? I love this job mostly because I can do what I want. I have no boss. I've worked in industry, and you're always answering to somebody, trying to. I'm not sure why this keeps ringing. Can I just take this off? Is that fine?
No.
All right. What's that? Okay. All right. Thank you. Yeah. So I don't really have a boss. I mean, Dimitri's here, but he's not going to tell me what to do. I get to decide what I want to do based on what I think is interesting and where I think a field is going and what I want to pursue, intellectually. There's really no other job like this, right? You talk to people in the real world with real jobs, they don't get to do all this stuff. It's a perfect mix of innovation, trying to come up with new things, mentorship, mentoring students, and then teaching, which is like this whole other side of things where you get to stand up in front of a bunch of people and show them something that they never knew before. And there's no other job in the world that's like this, right? I think people in our field, with a phone call, 24 hours, I could probably triple my salary and live on the beach. But, I don't want to do that. And the reason is that this job is just so unique. And I love the fact that you get to do all these different things and do what you want. And, you're not beholden to some sort of corporate bottom line, which you are when you work in industry. And the other sort of big piece of this is that you have an exponential impact. You go and you graduate students, and then they go off and do stuff. And you're creating these other entities in the world in the form of your students that are going off and doing fantastic things. And I have 4 of the students here that I've graduated have gone off and done that. Some of them have taken the money by the beach, and good for them. If that's what you want, I'm glad and happy. And some of them have actually gone on to be professors themselves, which is just kind of a cool thing. So what do I think is next? For our industry? Well, Moore's law is ending. And this is actually a great piece of information for us as architects. There's going to be billions made in the fallout. For decades, basically the big companies like Intel have been able to bury any really interesting architectures because they could always beat you on process node because Moore's law would kill you. Moore's law is dying. And we've been saying this for a long time, but now it actually is. We can't make these things any smaller, so we're going to have to find other ways to get you that efficiency. And that means changes in architecture, changes in systems, increased specialization. We're seeing that with accelerators. That's the stuff we do. We're right in the meat of what's going to have to come in as Moore's law dies, and that is super exciting. I've got tenure now, and this is happening, so what am I going to do in this space? I'm not exactly sure yet. I actually just got tenure, I think officially on August, right? I think it takes forever, by the way, if you're a student. Right? I think I submitted the package like 18 months ago or something. Anyway, but whatever. It takes a long time, but I officially got tenure, I think in August. And so, just trying to figure out what's next. I actually am intrigued by this idea of commercialization, just mostly because it seems like something that's a bad idea that maybe I should do anyway. But it's also kind of maybe satisfying to take a product and commercialize it, right? Because we're academics. We send things to journals and conferences. Other academics look at it and say, oh, this is interesting. But to really test something to see if it really is worthwhile, I think capitalism actually is a pretty good vehicle for that. I think, I hope. So that's something we're sort of thinking about. Many thank yous, my graduate students, some of whom are here. If you're not here, if you're not on this slide and you're here, just slack me a photo. Sorry, Nee, I didn't have a photo of you. And I think, Ahmed, I took that off GitHub. That's like a digitization of your face, right? So and my apologies because I put this together last minute, so I didn't actually solicit photos. But I owe everything to my students. Everything I've done as a professor, everything I've done in order to get tenure, is based on their work, and that's sort of the thing that I'm the most proud of is the people that we've managed to train and create and continue to go on to do cool things. And that's it. I think I did it in 10 minutes-ish. Thank you very much.
Thank you so much. I don't know about you, I learned a lot, including that we can lower team salary and it will still be fine. All right, so time for questions.
Yeah, for somebody doing system architectures, what do you think is going to be in my laptop in 15 years from now, and how do you think your group would have been contributed to that?
So there's going to be many different things in your laptop in 15 years. We're already seeing that. Right now your laptop is primarily a CPU and a GPU for the most part. They're doing most of the work. We're not going to be able to keep selling you new laptops with current CPU and GPU technology because of the fact that Moore's law is slowing down. So if we want you to buy new stuff, we're going to have to put new things in there that makes your battery last longer, that makes stuff last longer. So the diversity of things that you're going to see in your laptop is going to increase. And that's exciting from my perspective because we design hardware. So the more hardware designs that people are willing to pay for, the more innovation there'll be in that space, as opposed to everything just having to run through your Intel CPU, which it sort of still does today. So I can't say for sure what'll be in there. You'll probably, there are already machine learning accelerators in a lot of your phones, et cetera. So that's one piece that's already sort of working its way in. What's going to happen in 15 years? That's, whatever happens, we'll do something to try to make that better. But I think you'll see a vast diversity of different things inside your laptop in 15 years.
Thanks, Nick.
Very inspiring story. The question is on your little sad paper that might have generated many good papers now.
It was a good paper. He called it a sad paper, maybe to motivate me. I don't know, but yeah, go on.
But did it help you to generate creative ideas around it, how to make it successful?
Because it was a sad little paper? Yeah. I think so, because it was like, this thing is dying. I think it depends on your personality. I feel like if there's no sense of urgency, I won't do anything. Not everyone's like that. But I am. So I think the fact that it was a sad little paper gave me a sense of urgency that, hey, I better do something. But tenure's like that too, right? If you have to, you have to get tenure. You have to, do a bunch of stuff by this date or else you're not going to get it. So it definitely, deadlines focus people, right? And I think that that's definitely true for me. Yep.
Great talk. A technical question.
Mm-hmm.
So there's a lot of talk about, with the end of Moore's law, about advanced packaging and heterogeneous integration playing a more important role. What does that mean to a computer architect?
Well, it actually means a little bit of what we did in this middle project here, right? Where we're basically, chiplets are going to appear, right? We're going to package things and not these monolithic dies. We're going to have some kind of interposer that connects chiplets together. And we're going to have weird characteristics that we didn't have when everything was all happy and cozy on the same die, right? We're sort of going to, it's almost like we're going to go backwards. Because for decades, it was like, the IC, there wasn't much we could put on it. Then Moore's law came, and then everything went into the IC. Now, it's like, okay, we still want to put more stuff on here, but the IC can't get any bigger. So we're going to go back in some ways, and that's going to have all kinds of interesting challenges from communications perspectives, from how do you program something like that? Like, is your laptop always going to be composed of chiplets and all the software that needs to run on that? So I think it'll pose a lot of interesting questions. I think that this is true of a lot of fields in science. They go in cycles, right? I think we're kind of going to bounce back a little bit and have to look at things that were important pre-Moore's law, if that makes sense.
And one quick question. So if we're working towards efficiency of the design, how does that work towards efficiency of energy consumption on the chip? Is it possible for us to get the same amount of output with much less power draw in the future?
So it's been mostly that Moore's law has made that somewhat easier for us, right? Because basically the things get smaller, they get more efficient, and with the same design you can basically get more energy efficiency. What the argument that folks in my field make now is that as that ends, you'll have to get efficiency in other ways. So you'll have to, one very concrete thing that's happened today is specialization, where you have specific hardware components that do a subset of things very, very efficiently. But then how do you use the subset becomes a big challenge. How do you program those things? You can't just, dump down some Python and have it work. So I think that, I think to sort of answer your question, we're going to have to find ways to make things energy efficient without the underlying technology being better, which is part of the challenge.
Okay, thank you.
I think that was the last question based on the time we have. All right, let's give a round of applause again for Phil.
Thank you.